All right, so thank you for coming to today's lecture 4. So we may start our lecture 4 today. So we will have the lecture 4 entitled Amplifier Design and Amplification. It's about live demonstration. So how was CAD exercise 2? Can you share your opinion? Everything was okay? Clear? Wow.
Not everything clear.
Okay.
There were some descriptions, let's say, that at least for me make it quite let's say didn't make clear what it mean some requirement, and also what are suggestions and what are requirements. That wasn't clear for me, but overall for me it's always the matter of time, but that's another thing.
It's another thing. Okay. So maybe we will go through the CAD exercise 2.
That's a really good surprise.
So if you have any questions regarding specific points, please let me know and stop our lecture, and you can also ask questions. Thank you. Any other comments or opinions? Okay, if you have any other comments or opinions during the lecture, you can also ask a question. Okay, let's go through. Let me see. So as usual, lecture 3 video slides are available, and your learning is most effective again when you attend the lecture. And as usual, questions you can also ask question like this our nice colleague, but also you can ask question through Pressemo. So today's lecture access code, question access code is this 2553D6. Okay, so thank you for asking question last time. So someone asked this question. Could you share the lecture slides on my courses prior to the lecture so they can be followed on a computer? Sorry about it last time. So this time we uploaded lecture slide, so you can check through your computer my courses. So we will also aim the next time and the other next time and so on and so on. We will aim to upload the lecture slide PDF on my courses one day before the lecture so that students can open and follow the material on their computers while I'm speaking something. And CAD exercise 3 is out. Please submit a report answering the questions specified in the CAD exercise 3 instructions. So deadline is as similar to last time, almost 2 weeks later. February 10, 2026, 11:59 p.m. Helsinki time, and late submissions will be graded with half score multiplier. And for the quiz, there is an update on quiz retake policy. So again, please help us grade your quiz accurately by writing clearly. And this is a quiz retake policy. Only one retake per quiz is allowed. So there is no multiple retake. And the retakes open only after the quiz solutions are released. So after we release our quiz solutions and how to solve the quiz, then we will you can take the retake. And retake questions will be different with a bit higher difficulty level. And the retake takes place on Monday, no other day. Your final score will be higher on the 2 attempts. So you can, it's fine if you scored lower score, but if you score higher and at retake, or let's say your retake score is lower, then don't worry, no losing of any score will be given to you. And your final score, on the next Monday, the next Monday, February 2. So quiz 2 retake will be held. So there's no quiz 1 retake. There's no quiz 3 retake. So let's go through the quiz one. So that I couldn't explain clearly last time.
Thanks. Should we each one arrange personally, or is it like that there will be specific time?
Yeah, this is a specific time at or once. So on the same time, on the same day for the retake. So our TAs will try to find some time frame or some time slot on Monday that everyone can take the quiz. For example, like to avoid any overlap with other courses, maybe like 5 p.m. or 6 p.m. can be possible. But our TAs will communicate. For those people who wants to do the retake, please let our TAs as soon as possible, such that you won't lose any opportunity to do the retake of quiz 2. Are you feel hungry?
No.
No? Okay. Okay, so let me explain this one. So last lecture I couldn't describe clearly. So this one was cosine, it can be described as a cosine, what is happening? Cosine 2 pi ft. This is a general equation or expression of our phase, right? So after sampling, as we did in our RPS or FPS question, we can actually substitute this time. Now it is not continuous time. Now it is a discrete time. We can substitute with 1 over fs, 2 times over fs, 3 times over fs, and so on, such that t equal to n over fs. Then after substituting this one, then we get 2 pi 150. So 150 is hertz, right? 150 hertz. And when we substitute this one, t, then we get sampling rate, 600 hertz and 150. So this is it. So this doesn't cause any aliasing. On the other hand, for the high frequency, like 450 hertz, that goes over Nyquist rate, 300 hertz. Then when we substitute t equal n over fs, then we get this. So we can actually further process this equation by plugging in 450 equal to 600 minus 150. This is because we are focusing on this factor. For the phase, every single trial on 2 pi with the multiple integer times of 2 pi, that goes to the exact one rotation, right? 360 degree. Then it goes to the same value, cosine phi. So when we do this, then this part cancels out. Then in the end, we get this one only. So negative 2 pi 150 over 600 times n. So it goes to the same situation as 150. So this is a one way around. What I wanted to let you know. So what are we going to run in lecture 4? So in lecture 4, I will go through C8 exercise 2. So we can go all together. C8 exercise 2. I will do the circuit design and run the simulations. And amplifier design performance validation will be carried out. And interpreting amplifier simulation result will be also carried out. That will be helpful to do CAD exercise 3. Okay, before we go to there, let's have a look on quiz 2 first. So this is a score distribution. There was only one person who scored perfect, 20. And this is initial quiz 2, and this the right side graph shows the score after retake, the first retake this Monday. So the average score increased from 10 to 12. Okay, then let's go through quiz 2, question 1. So this is about unbuffered filter parameter analysis. And I believe this one was a bit easier if you took the prerequisite courses in bachelor level. So for individual time constant, tau 1 and tau 2. So for time constant, we call this as a RC time constant, which means that when we multiply R and C, it goes to dimension of second. This is the reason why we call it the RC time constant. And for tau 1 and tau 2, it can be simply derived by multiplying R1 C1 and R2 C2. That's it, tau 1 and tau 2, right? So solution, we can just simply multiply. So R1 is 1 kilo ohm, C1 is 10 microfarad. So here, it goes to 0.01 second. Or tau 2, 4 kilo ohm and 2.5 microfarad. So 4 kilo ohm, 2.5 microfarad. So it goes to 0.01 second. And the natural frequency, omega 0. Remember, we calculated this one as R1, C1, R2, C2. This is omega 0, right? So we can simply do tau 1 times tau 2. Oh, sorry, it should be 1 over. So it should be 1 over square root tau 1, tau 2. That goes to 100 radian per second. And loading time, R1, C2 in seconds. This is also same, similar calculation you can do. 1 kilo ohm here, and C2 is 2.5 microfarad. So it goes to 2.5 millisecond. And coefficient, the total coefficient of S term. You can do some calculation about this transfer function, but if you remember, then we calculated something in transfer function, something, let's say, A times S squared plus this term we observed in the unbuffered RC filter, that R1 C1 plus R2 C2 plus, and we discussed who are you thing that is affecting R1 and C2, right? R1 C2. So this is a R1 C2 loading term, right? So in denominator, we can describe by this coefficient by tau 1 plus tau 2 plus R1 C2. That goes to 22.5 microsecond. And for the Q factor for this unbuffered circuit, if you remember, then the Q factor can be calculated by solving this equation, right? So I guess it was like R1, C1, R2, C2, and the loading coefficient. This is a Q factor. So coefficient here and square root tau 1, tau 2 here. Then it goes to 4 over 9, or if you numerically further calculate, it goes to 0.444. And for quiz 2 and question 2, realizing second order Butterworth filter with RC component. So this is a Butterworth filter transfer function, right? So we take Q factor 1 over square root 2. This is how we describe Butterworth filter, a second order Butterworth filter, then prove that passive RC circuit shown in figure 1. I think there was a figure 1 showing our circuit here. This RC filter cannot realize second order Butterworth low pass filter. This can be simply proved when we calculate the Q factor and the maximum value of Q factor that we discussed in lecture 2 and lecture 3, right? So deriving the transfer function and calculate Q factor, and when we apply the arithmetic geometric inequality, then we get 1 over 2. So Q factor cannot go higher than 0.5. That cannot build any other Butterworth or more complicated filters like Butterworth, elliptic, or Chebyshev filters. And question 1. So so retake question 1. So there is a bit different circuit for RC circuit, right? And the questions are very similar. So calculate the time constant, tau equal RC, when we take R1 equal to R2 and C1 equal to C2, then we can simply calculate RC, right? Here, RC. I believe you can do this. And the Q factor for the filter when stages are directly connected without buffer. So like this. So this is exactly same situation in quiz 2, question 1, right? Here. Then, because we have R1 equal to R2, C1 equal to C2, then the Q factor it goes to 0.333, right? As we did in previous calculation that I did. And for the Q factor of the filter, if an ideal buffer is inserted between here. So now our situation goes to exactly this situation. Like above figure, and we take this buffer as an ideal. Then it goes to simply, there's no loading effect. Then it simply goes to RC circuit, cascaded each other. That goes to, just for Q factor equals to 0.5, which is a maximum value because we have R1 equal to R2, C1 equal to C2, right? And for the calculate the percentage increase in the Q factor, you can simply calculate, right? How much we increased from 1/3 to 1/2, then it goes to 50%. And determine the new S-term coefficient for the buffer transfer function. For this one, you can calculate the S-term coefficient as we did for the coefficient in quiz 2, question 1. Then it goes to 2 times RC constant. That goes to 0.002 second. Yeah, for the question 2, we typically analyze simple RC, first order RC low pass filter as we discussed in lecture 2. This one, right? Using a voltage divider rule, then we can get transfer function. However, in this lecture, in lecture 2, we modeled it as a negative feedback system involving an integrator. Then why a passive RC circuit can be viewed as a feedback loop? In your explanation, identify what physical component acts as an integrator. That we discussed, right? Capacitor acts as an integrator. Integrator, because its impedance or impedance goes to 1/SC. So capacitor acts as an integrator. And what physical mechanism provides the feedback subtraction? Remember? If you remember, then the negative feedback system, I think something is wrong with my mouse. Let's say this one is A. Then this one is beta. Plus minus. So in, and this is out. So this is a feedback system. And for this RC circuit, when you solve the nodal equation, nodal analysis, then the current going through this side, it goes to, so let's take this one as an in and this one as an out. Then the current goes to this direction. It goes to in minus out over R. So there is a subtraction, right? So in here, minus out. So when we take beta equal to 1, then this one also equal to out. So there is a subtraction in minus out. So there is a subtraction in current equation in minus out over R that goes to current. So current is actually caused by resistor. The subtraction, physical mechanism provides a feedback subtraction is caused by resistor and the current. And draw the feedback diagram and match the physical components, resistor and capacitor. But then we can also draw this feedback diagram. And now A equal to what? So 1 over SRC. A block and beta block equal to 1. And describe the negative feedback mechanism of this RC circuit. Start your description by answering this question. If V out rises, what will happen? So if V out rises, maybe I can select other color. So if V out rises, then what will happen? Then the current going into this direction is decreased because we are subtracting input and output. Then the current is reduced, and the amount of the current that is multiplied with impedance, which is 1 over SC, is reduced. That goes to V out value going down. So there is a negative feedback mechanism here. So this is a solution. You can also check the solution from my course's website. Mm-hmm.
Question 3. In the question, asked you to do a feedback block diagram, and the answer says that it's error. So the question here on the third one asks you to create a feedback diagram, and then the answer on the next slide talks about error thing.
This one is just evaluation criteria. It doesn't directly match one-to-one. No worries. So if you solve exactly as it is required, then you will get the full score. Yes. So you can also check your quiz score from my courses. It is online. Okay. Then we can move on to CAD exercise 2. So let me open our template, report template. So we designed our amplifier, single stage current mirror amplifier, right? So there are some questions to answer, right? Here and there. So, okay, let me open. Okay, so to answer that question, before we answer this question, let me build the circuit first. So let's make a new library. Here, you can select this one as a new library. So let me give a simple schematic name. So let me first build amplifier design. So we can call MOS1 board. I guess everyone knows how to call instance, right? Add instance. By pressing I. Then we can call add instance here. So what I suggest when you design any analog circuit as a starting point, unless you are touching really ultra high frequency like gigahertz or terahertz, then you need to take extra effort. But if you are just staying just some low frequency signal like less than, let's say, 100 megahertz or less than 10 megahertz, then what I suggest is just set length and width as a 1 micron. This is very simple approach. And if you set the length as a 1 micron, this is a very large length and good enough length that you can approximate that there is no short channel effect. That goes to very easy and theory compatible design approach you can make. And then if you press space, then you can, as we discussed, you can automatically attach all the labels. So space instance selected. space. Let's call it this way. Attach labels. And if you do T, then edit label. So if you press T, then you can change the names. So this side I will assign in, and for this side, let's say VDD is connected, and I will not add any label here because this will act. Oh no, sorry, it should be PMOS for the input transistor. Again, it will be very, very simple design. So I will just simply assign 1 micron. And here. So Shift M, then move instance. And ignoring connection. And M is a move instance. So let's put it this way. So if I just move this label, then it goes like this by using only M. But if you use Shift M, then you can, move this label only, ignoring any other connections. So this one is very helpful. And I'm gonna select VDD, but it will make reading not. So I will identically clipped the label. So here I can say, so let me see, what did I do? So here, right, Ctrl R. So Ctrl R, it goes to vertical flip. So we can connect this way, and we can assign the source side as VSS. Let's make sure it doesn't block our label, and then Shift R, it is a horizontal flip. And there is a diode connection. And it's also useful. Instead of being always, oh, what is going on? Instead of using a mouse always, you can do zoom in and out by pressing this mark. Okay, so for the load part, I mean not load, so current mirror part. Yeah, so for the body connection, if you are sure you are connecting body to the source, then you can simply tie this body to like source. This also works. Let me zoom in further. So instead of doing this way, you can also do like this. This is also completely fine. So W is wire and U is undo. And I think if I do this, U and Shift U, you're right. And Shift U is, I think this was redo. All right. So we can attach VDD here. And so we assign this side input P and this side input N. All right. Then Shift X goes to save schematic. schematic shortcuts. And let's assign this node as a bias. Okay, that's it, right? And if you P, then you can add pins. So P, add pins. So what I do normally when I design analog circuit, I just simply select input and output for all the pins. So VDD, VSS, input P, input N, VB, and out. So this way.
So no more specification of
It's not required to pass tape out and DRC or LBS. But if you want to make sure, okay, I want to make this pin specifically for input, specifically for output, then you can do it. But if you connect the different terminals with different feedback configurations, for example, sometimes gate acts as an output of any terminal. Then if you select this one, input N as an input only, then you cannot connect other circuit as an output connected to here. And then this node becomes output terminal, output node, and as well as input node. Then Cadence Bot also send you some error message or warning message. Sometimes it becomes a bit cumbersome to design efficiently. So I just decide to give input and output for all the pins, but it takes it takes your own risk.
Okay. And then there was also on this screen there was like that. Is it signal? Is it power? Is it different further options?
You can just simply assign input and output. That doesn't make any significant error, significant warning.
Okay.
Yeah. And then after that, we can make symbol, right? For symbol, what I do is just pressing Alt C, C, and C. What it means that if you go, we can go to create cell view, and from cell view. This is, but rather than using this way, so Alt C, 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 then it goes to create a symbol. So Alt CCC. What is happening here? So Alt CCC. Then it goes to like this. Let me see. Alt C, C. Okay, then Alt C and C. Okay, then you can simply press OK and OK for everything. Then you will generate a symbol like this. So let's make amplifier diagram. So we do this way. And what I prefer for, this is my personal choice. So I don't like this giant pin size. So what I do is I just select round here, input and output. So VDD, VSS, input P, input N, VB out. Instead, it goes to smaller, miniaturized. Size, VDD, VSS, input P and N. Yes, we can attach this way. And VB, maybe we can put it this way. And we can delete all of this. Path name, instance name, and we can delete. So this is first I will explain what did I do for removing the red box. I will explain it. So this is it. And then if you go back to schematic or if you go back to symbol, you can press equal sign. I mean equal keyboard key, like here, and switch to symbol or back to schematic. What it means that if you press equals keyboard, you can go back to schematic, you can go back to symbol easily. Okay, then what I prepare for testing this kind of circuits, I make another schematic with TB sign at front. This also aligns with how digital circuits are tested, TB underscore amplifier. And then we can instantiate or add instance by pressing I, or maybe do this way, amp. Then we have this amplifier. So now we have mouse pointer here, but amplifier is far away. I mean, a bit away from our mouse pointer. So let's instantiate anyway. This amplifier structure, and this selection area is a bit odd, right? There is nothing in this area, but there is a selection area expanding this much. This is because of this one, instance name. So this instance name box is this much wide, such that it causes the selection area like this much bigger. And also if I put this symbol mark further away, then what happens is that if I instantiate amplifier, here you can see that it's too much far away, and it doesn't make our life easier. So what you should do is that first you have to create a selection box, and just press automatic. Then it automatically creates selection box. This red area is the selection area. So if you go back to our test bench, now you can see the yellow area for selection. It goes to more compact within our symbol. And you should also put origin that close to our amplifier side. So this will make sure when you add instance, it will follow to your mouse pointer. So what I prepare is I just put origin to the VDD node. Or if you look to put origin to VSS or output input or even center, this is also fine. So if I instantiate, and now you can see that our mouse pointer is centered to VDD, and selection box is more compact. Okay, then let's see. So height. So let me first satisfy this target task. Like transistor length, it is already set as a 1 micron, right? So let's run this open loop DC gain. So before we run any AC simulation or any other simulations, first thing you need to do is make sure this amplifier or analog circuit is under the correct DC operating point. So let me build test bench for that. So I can assign 0 for this one, ground, VSS. This one goes to VDD. Yes. And we can assign supply voltage as a 1 volt. Then it goes to VDD, VSS. And as it was introduced in the document of CAD exercise 2, we can build ideal balloon for the differential circuit simulation. We can put quiz sign here. So AC magnitude we can set as a 1. It doesn't mean that we are physically applying 1 volt, but we are applying a unitless voltage that will be helpful for getting AC signals. Let's put it this way. And you can assign this one as a VDC. Input P and input N. The input P and input N. So those yellow mark, these are all 1. It doesn't mean that there is something wrong or there is something error. Oh, if you have a question?
Just that at some phase, if you can explain a bit the rationale behind the balloon usage here.
Mm-hmm.
If you can at some phase explain what is the idea of the balloon and.
Oh yeah, I will explain it. Yeah. Any other questions so far?
Yeah. Why do we need like 0 volt DC?
0 volt DC. Yeah. Instead of just using ground all places. This is yeah, just create to BSS. It will be easier when you design more complicated chip later. Then you have to pass LVS, and you have to manage other like digital circuit BSS and analog circuit BSS. Then it becomes a bit complicated if you assign those. This one is a ground, a global ground. That is globally organize all the simulation world. So if you just set all the global ground for every single places, and it may make some small mistake.
What is it required? It's good practice.
Yes, good practice. It's not how to say strictly required to do this way. It's a good practice to avoid mistake.
Can it be that we just connect ground and VSS cable?
The cable.
Without the
this one.
Yeah.
I haven't not tried it. Maybe we can try.
I tried doing that like modified nodal analysis errors.
Errors. Okay.
Like made the matrix singular.
Yeah, I guess that was caused because we are trying to. I mean, this one is a global ground, so that it already has some label. If we force connect, for example, if we let's say we gave a label name of VSS, then it will cause some errors. So this is not allowed to change your label name and so on and so on. So for this one means that there's no connected any how to say an instance. For example, if I even like connect wire like this, it will also cause warning, yellow warning. It's that there is no instance connected to this node. So anyway, let me first complete this connection. So GPK PMOS. For this time, let's simply make the current meter setup. And here we can assign current as a 1 micron, but you can choose smaller or larger current, depending on your design. Then when this one wait, then warning goes away. And for the output, by default, you don't need to connect any output nodes, such as like capacitor. By default, you don't need to connect unless it is really, really necessary. like this. You don't need to connect like 1 picofarad or 1 femtofarad or 10 femtofarad. So by default, so if nothing is connected, then what I suggest is you can instantiate this one. So it means there is no connection. So you can terminate output node like this, then all warning signs are gone. So let me explain this one first. So here, let me call ADL. And if I do this copy from cell view by clicking right click, then you can you can call all the parameters that were used in this schematic. So let me simply assign half VDD. And for this one, you can actually assign a variable for this stop time. So for example, if I set bar variable key trend, you can see that there is a variable assigned here. So the reason why I am assigning this kind of variable is that we can assign here frequency such that let's say F in and amplitude maybe just 1 millivolt, very small enough. Go back here, F in, let's say 1 kilohertz. Then we can actually assign this T trend that is proportional or that can be controlled by F in. So for example, if we want to just look at 5 cycles of F in, then we can divide like this. Then it goes to, the transient simulation time can be controlled by a variable that is controlling the input frequency. So if I just run this, what is happening? Maybe I save it. And if I run this, then it goes to simulation. All right. So for my case, I customized the shortcut to call main form. So instead of going to this and this, I actually customized by pressing the number 4 key. Then we can call it. I will let you know later after this lecture how to do this. So main plot shortcut. I think it was main form. So anyway, so if we click input P and input N, then we can get this. So I can send to ADE such that the output are assigned this way. And before I further explain, I will expand this one and then run the simulation again. And let me change this accuracy default by to conservative. So currently the simulation edges are a little bit sharpy. This is because the number of points are too less. It's a very sparse number of samples that are simulated. So if by default, this is because by default transient simulation goes with the lowest accuracy level. So if you select this one, so from liberal to conservative, it goes to more accurate simulation. If you run this one again, then it becomes more smooth edges. You can see that. And then if I plot this node, input node, and let me move this plot to lower side, then you can see that its amplitude is actually here to here. It's actually 1 millivolt as we assigned here. We assigned 1 millivolt, right? Amplitude. For the input signal, I assigned, I plotted this node as an input. By the way, if you like to have a view of this difference, you can waveform viewer cut. Then A and M. Difference marker. No. So if you press A at this point, if you press D, sorry, it's a D. D. Then you can see the peak-to-peak value right here. 2 millivolt peak-to-peak, 1 millivolt amplitude. So what about input P and input N? So now we are applying VDC equal to 500 millivolt. So those are input P and input N are generated around the DC value of 500 millivolt, and both of them have the peak-to-peak value of 1 millivolt. This is what it means. So if I plot the differential net, input P, click once, and input N, click, then we can plot differential amplitude. Then the differential amplitude becomes exactly same as this input node, the input of the ideal balloon. Input P and input N, right? It goes to 2 millivolt peak to peak. So the idea about this ideal balloon usage is setting up some simulation environment for the differential circuit. So this one is generating small signal that are split out with a VDC value, DC voltage shift, and having two signals that are opposite polarities each other. Okay, then if you have any question, please ask. Okay. Then we can move on to AC analysis. What I do is just simply assign 1 to 1 gigahertz. And we don't need to run transient simulation at this moment. And we have to run DC simulation. Then if you want to inside this schematic, you can press E. Then it opens descent. Or if you press Shift E, you can also descent. The only difference is that you can open for edit mode for Shift E, and you can open for read mode for just E. Descent and Shift E. Send on read mode and edit mode. So let me open this schematic with read mode. Then you have these parameters. So to show the DC operating points, you can use this option. Then we can see that there are DC operating points, but those are overlapping a little bit. So maybe we can make it further apart. So we can see that VDS for all transistors are secured for larger than 200 millivolt, except for this guy, this one, 105 millivolt. So what is recommended when you design analog circuit in this kind of simple circuit, unless you have further optimization requirement, then it is recommended to secure at least like 200 millivolt VDS or 150 millivolt as a lowest. So to make sure, so it is blocking our value. To make sure this VDS is secured. So what is required to do is that we need to lower down this node, this node, this yellow node. So do you have any idea how to make sure this node is lowered? So what did you try? Go ahead.
Increase the width of the input CMOS.
Yes, yes. Oh, what is the reason? Can you explain?
On full disclosure, I just messed around.
Any other student who knows the answer? Mm-hmm.
Reduce the voltage.
Which voltage?
Yeah, you need to reduce the source voltage.
Source, yeah, source voltage here, this one.
Yeah.
Yeah, so to reduce this one, what should we do? Increase the width. Yes. Yeah, reduce the resistance. Oh, yes, yeah, that's a nice point. So reduce the resistance, or yes, there's also, those are good points. So what I'd like to explain in the other way around is that, if you remember the current equation of the transistor, although those transistor looks like it may go into subthreshold region, but let's assume that all the transistors are strong inversion and saturation. Then it goes to half mu and C oxide width over length VGS minus pre-threshold square. Do you remember this equation? Yeah, this is transistor's current equation, right? So let's assume that this bias current is holding the bias current very tightly, such that it governs the bias current, like in this case 800 nanoamp. So those bias currents are split in each side with equal magnitude. So the bias current, let me change this color. So bias current, this one is fixed. Then what we are currently targeting is that we need to lower this node. Yeah, you need to lower this node, right? So this one goes to source node of input transistors, source node. Source here, VGS. So what we need to do is maybe we need to reduce VGS because the gate voltage is fixed by the DC input voltage, 500 millivolt. So we want to reduce VGS, voltage difference between gate and source. In this case, when we increase the width, assuming all other parameters are fixed, then the only way to make sure our current is fixed is that reducing this VGS if we increase width. This is how it works. So let's verify our idea. So we can select both of transistors by pressing Shift and left click. Select multiple instances, and Q is edit instance options. Then we selected both of transistors. Then when we want to make sure both of transistors are affected all at once, such that if you, for example, assign like this 10, and let me go back to parameter. Then you can see that only this transistor is affected. So otherwise, other than this way, when you select both of transistors and Q, and if you change this option, apply to all selected, then by changing something, then both of transistors are affected. And let me remove this. So for changing this finger and the finger width, what it means is that there is a transistor that is physically placed. When we change this number of fingers, then it means that we are attaching the copy and paste numbers. I mean, of the copy and pasted transistors of the unit cells. This is the meaning of finger. And when you change finger width, then you are increasing the width itself. This is the meaning of changing the width. So you can choose whatever you feel like to do, but it will change how you will do the layout later. But what I prefer is just changing this number for simulation purpose because it's easier to change. Otherwise, we have to, mouse point here and then put 10. This also. So anyway, let's change this way. So 1, 1, 10. Okay, 1, 1, 10. Oh. So if you run the simulation, then you can see that this source node is decreased. This is how it works for the transistor sizing. And there I can let you know how to further decrease this node by applying some more techniques. For example, so current equation is proportional to VGS minus bridge threshold square, right? For threshold voltage, there is a body effect. If you connect body node to some other node that is not connected to the source. In this case, if the source node and it's not easy to show. So if you connect body node that is different from the source node, then threshold voltage increases. Assuming that this body node for PMOS transistor is higher than the source node. So that makes threshold voltage high. That also makes VGS goes high because we want to make sure current is fixed. So if you connect VDD node to source node, then you can further lower this node voltage, right? Because now it becomes 809 millivolt. And if you really want to further lower down that node, you can use low threshold voltage transistor. So the key point is that we want a lower threshold for the transistor. So it's, the transistor performance is a bit different from normal. So you can see that, okay, source node is reduced down to 760 millivolt. But in this case, it will cause a higher leakage current and other like noise and other performance parameters may be different from the regular transistor. So it must be used with extra care. But if you aim to just lower down this node anyway, then you can simply use this method. So anyway, let's go back to our original configuration. Let's make it back to 10. Okay, then it becomes 828. Now it becomes 171 millivolt. So if you further reduce, if you want to further reduce this, if you want to further reduce this yellow node such that VDS is more secured, then you can further increase this width or attach this body to source or reduce the input DC voltage, like DC voltage range, 500 millivolt. Okay, then that's it. And because we have run this AC simulation, you can plot magnitude here and also phase. So this is an open loop simulation result. maybe we don't need to plot 1 Hertz. Then you can see that, okay, its gain is 30 dB, and it goes down more and more and more as frequency goes up. And the phase starts from 0 degree and goes down like this. Any questions so far? I believe no. Okay. So I guess we went through schematic and symbol, test bench, and DC and AC simulation. So laser point. Okay, so we can have a break. So please, if you can, please check in attendance by scanning this QR code. So we will have a break until 9:30.
How much freedom do we have to change? For example, in the description of the CAD video, CAD 2, there was a specific current source value that was like 5 times what you used here.
What was there? The specific current consumption? You mean the power consumption requirement?
I mean that if I could modify this, I would have much easier I suppose, much easier the
Okay.
Power consumption, because there was fixed that it's, was it how many milliamperes was, or
I guess
I
it
don't
was.
remember. I think it was 5 times what you used.
Can you show the CAD exercise there?
I'll try.
Okay.
So there was specific.
No, this one.
Yeah.
This one. This one doesn't mean that you have to follow the 5 microamp.
Okay.
Okay. Based on this one, you thought that you need to set 5 microamp.
Yeah.
You thought it. Okay.
And then when I consider that I can't modify anything that is given, so that I could, at least as I understand it, for example, if I didn't have so much current from here, I could lower the consumption.
Okay,
that
okay, I understood. So, everyone, can you answer? Did you guys thought this 5 microamp is a requirement? Then you have to follow it. Okay, then this was not intended to force all of you to follow 5 microamp. It was for example. So then in this CAD exercise 2, we will not lower any score if you couldn't make it like power consumption less than 10 microwatt. So sorry for misunderstanding. So this one was intended for showing example value. So as long as you satisfy the target specification at the end of the template, there was a table, right? Then that's all fine. Then you don't need to worry about. And also we will not, cut down score, the evaluation score, even if you couldn't make it like less than 10 microwatt.
The length should be less than the 1 micro.
More.
Oh, more. Yeah, higher.
Yeah.
Yes. 1 micron.
Greater or equal. It's greater.
It's greater. It was greater.
Yeah.
Right. Right. It should be equal or greater. Oh, sorry about it.
Yeah,
You mean this one?
Things are what I. There
Ah.
are some things that are not clear or.
Okay. I agree. Thank you for raising up some shortcomings of CAD exercise 2. So issue and power consumption issue. Okay, then so we will then extend the deadline to the end of this week for CAD exercise 2. So all of you can make sure the correct procedure following and to remove or drop down any misunderstandings. So yeah, if you in the next CAD exercise 3 and 4 and so on and so on, if you have any questions, please ask to our TAs or to me if you have difficulties, or it is really required, or is it suggested, or is it just recommended, and so on.
Just practically about this, is it possible to have even once per day, let's say, to have some kind of forum that we can put while working for the project?
Yeah. So you can.
So that at least once per day, or I don't know how often can be, that we can get some reply on such kind of questions.
Yeah, so in my courses, there is a discussion forum, so you can post any questions. Yeah, you can
do it like that.
Yes. Maybe I should mention discussion forum in the next lecture. Okay, then let's start our design. All right. So for upload DC gain, we made sure rather than 30 dB, right? It was a 30 dB. And upload bandwidth, so this DC gain is just 30.8 dB. So let's assume that we are measuring 3 dB bandwidth, so it goes to 27 dB, and it was 37 megahertz. So it's larger than 10 megahertz specification, requirement, right? Where is it? Here, larger than 10 megahertz. So let's move on to the stability simulation. For the sake of simplicity, let me assign this one as output 1, as this one as output 2. And you can instantiate to simulate the stability. You can instantiate iprop here. Important to note that you shouldn't connect input P for simulating this kind of single input amplifier design. So let me show you why. So if you measure dB scale gain from input to input P, then you can find that, okay, it has a -6 dB attenuation. So this is because we are splitting input AC magnitude to differential signals, and its difference, input P and input N, such that its difference becomes as same as this input voltage AC magnitude. So now it becomes 0 dB, which means gain equal to 1. So in this case, we should connect these input nodes to this port to make sure the correct can be carried out. And let's run the stability simulation, STB, and we can select this way. CSS, right? Okay. All right. Oh, sorry. Can you continue your discussion after this lecture? Thank you. Then we can plot magnitude and phase of this loop response. Then we have it. So we can see that it's a loop gain is happening something wrong, 5 dB. Oh, okay. I got the meaning. I got the reason for this. So we can see that its DC is connected to 0 volt. There's no DC offset for the input voltage. So indeed, we have to connect this DC voltage such that there is an actual deep set can be applied to this way. Okay. And for the analysis, we can add to output. Click this one. If you go back to ADL, you can see that dB20 and the loop phase are, added to the simulation output. We can call this way. And if you click this button, then you can plot it. So, okay, so loop gain is almost as same as 30 dB. That is close to what we simulated for the open loop AC gain, right? So what is the interesting point for simulating this kind of circuit is that when you plot loop gain and AC gain all together, base, and let me reduce this scale to like 10 kilohertz maybe. And you can see that this 0 dB crossing point, right? It's 43 megahertz. And actually this one is very close to what we are measuring to like 3 dB bandwidth. Like even if there is some deviation deviation from 27 dB, but it's very close to. So this means that there is a feedback loop, and as long as there is a feedback loop, this much loop gain here, this range, then this unity gain buffer works as buffer. So it determines the unity gain frequency of the loop gain. That determines directly the 3 dB bandwidth of closed loop response. That is a key point of this feedback analysis. So, okay, then let me go back to our sheet. So STV loop gain should be larger than 20 dB. Okay, right? For the phase margin, for checking the phase margin, you can simply go to direct form plot STB and phase margin, right? It says 49 degree. And if you click this one as to outputs, your phase margin can be also outputted. So if you, sorry, if you enable plot for phase margin and press this one, then you can see the phase margin value there. Anyway, so we need to do some compensation to make sure phase margin is good enough, like 70 degree, right? For this case, we can instantiate capacitor. So as we described in the CAD exercise 2 document, the recommended start is 1 femtofarad. So 1 femtofarad, what is this specific value of 1 femtofarad? The range of just one single gate of digital circuit. 1 femtofarad to 10 femtofarad. That is single gate input capacitance of, for example, inverter or NAND gate. So it's quite small enough. Anyway, so basic margin is still not good enough. So we can increase 10 femtofarad. Let's disable this loop gain and loop base, or maybe we can enable. And if you click this one to replace, then when you run the simulation, then the new plot will replace the previous result. If you change this plotting mode from replace to append, then if you run new simulation, then will be appended rather than replacing the previous simulation result, like this. So you can trace how it goes by changing the parameters. Right? And you can see that, okay, its margin is now increased to 68 degree. So maybe we can increase to 60 femtofarad. $70 degree. So what I'm doing for adding capacitor at the output is the dominant power compensation. This is because you see that here, node and node. All the internal nodes from input to output, from input this side, from input this side. All the nodes except for output have resistance value 1 over GM, right? This one is also 1 over GM. This one is also 1 over GM. And for output node resistance, what is the value? Do you remember? Output resistance? Yes, correct. So RO1 parallel RO2, or we can also describe GDS1 parallel GDS2. This is a parallel resistance. Anyway, if you remember, GMRO is much larger than 1 in classical amplifier design. Then RO is much larger than 1 over GM. Then what it means is that this node is a low resistance node, low impedance node. This node, low impedance node. This node, low impedance node, because RO is much larger than 1 over GM. This output node is high impedance node. So high impedance means that omega is equal to 1 over RC. If the impedance is high, then it's omega, which is a pole frequency, is low frequency, right? So we are adding capacitor at output node to increase C, such that its dominant pole is more closer to low frequency to compensate our stability. This is part of the study that you probably have studied in prerequisite courses, for example, basics of IC design. So let me go back to here. So what is happening here is that it's not easy to understand what is going on here. And here, so 0 dB crossing is reduced as we increase the capacitance from 43 megahertz to, let's say, 20 megahertz. At this point, we can see that, okay, the phase margin becomes from low frequency, low base crossover, the low base response to high base response. This is what is happening. And, or I forget. So H is horizontal, let's say, line marker. And V is a vertical line marker. Okay, so base margin is secured. And what else do we have? So the DC input range. So we asked in the document of DC input range can be defined as long as the DC loop gain is secured larger than 20 dB. Of course, if you go to industry or PhD course, then you will have different specifications to define DC input range. But for this simple CAD exercise 2, in our case, we simply decided to define DC input range for the specification that it can ensure the loop gain of unity gain feedback is larger than 20 dB. 20 dB, it goes to gain factor of 10. So let's go back to our ADL and let me sweep the DC value. So we can simply sweep to 0 volt to 1 volt, let's say 10 steps. And we are sweeping loop gain. We are sweeping VDC and plotting loop gain, loop phase, and phase margin. And let's see what happens. Let me change this plot to replace and replot. And it goes like this. Okay, so let me, okay, there is some error. I mean, this Cadence portrait sometimes have some bugs. Then when you sweep the voltages, it doesn't show all the points that is simulated. In this case, you need to run the simulation again. It's still 4 points only. But anyway, let's make some analysis of this loop gain. And we can change the VDC value later. Anyway, so if you set VDC equal to 0 volt, then obviously the amplifier doesn't work at all because 0 volt should be buffered to the output, and the output voltage is 0 volts, then output NMOS doesn't work. Its VDS is 0 volt. So it doesn't make sense. So we need to, cancel, drop this option, VDC equal to 0 volt. Then all the other cases, for example, 0.1 volt, 0.777, whatever, 0.8 volt, all these voltages can satisfy larger than 20 dB loop gain. So maybe we can drop 0 volt. We can increase 0.1 volt. And let's run the simulation again. It looks a bit better. Yeah, so for the DC, for the loop gain, we can see that all the conditions from 0.1 to 0.3 volt is missing. But anyway, all the conditions can be satisfied with rather than 20 dB loop gain. And the phase margin, there was a little bit decreased the phase margin at this specific point, 0.4 volt. You can increase, CL maybe 65 femtofarad and 400 millivolt. Then I guess it can satisfy the phase margin, right? 70. So when you run the simulation from 0.1 to 0.1 to VDD, it doesn't make sense actually, right? Because if you set 1 volt as a unity gain buffer, then the PMOS at the output, it doesn't work because VDS is 0 volt. So when you run total steps 0.1 volt to 0.9 with 9 steps, then it will run the simulation with 0.1 volt step. Yeah, I'm not sure what is happening here. But anyway, you can see that all of these conditions can be satisfied with larger than 20 dB loop gain. So we may define, okay, our DC input range can be satisfied with 0.1 volt to 0.8 volts. But there is another specification, right? The loop gain, open loop bandwidth larger than 10 megahertz. So we may remember back to what we discussed previously. The open loop bandwidth can be determined by the 0 dB unity gain frequency of the loop gain, right? So if you set 0 dB of the loop gain, then we can actually indirectly determine what is 3 dB bandwidth of the open loop amplifier. So this one is out because it was like only 1 megahertz. So we may define, okay, our input DC voltage range is 0.1 volt to 0.6 volt. All of them are satisfied with rather than 10 megahertz. Right, 10 megahertz. And to verify further, maybe you can set like this. Okay, so all of them are, except for 0.3 volt point, but anyway, all of them are satisfied with nicely rather than 10 megahertz 0 dB loop gain, which is unit gain frequency, and the loop gain is rather than 20 dB, right? So the total power consumption, you can measure it by clicking this one, or you can simply read out this value. So it says 5 microamp. So you can ignore this negative sign. It just simply means that there is a current drawing out of this voltage source. So the absolute value of this current consumption for both sub amplifier, it goes to 5 microamp. And remember, we set the supply voltage to 1 volt only. Then it goes to total power consumption is 5 microwatt, including both sub amplifiers. So divide this value by 2, then we get like almost like less than 3 microwatt. That fully satisfies our specification, less than 10 microwatt. So for the slew rate, we can set V pulse, and the voltage, as we simulated, we can set 0.1 volt, 0.6 volt. This was our input DC voltage range that we defined. And the delay time, we don't need to set it. Rise time, 1 nano, 1 nano. This is arbitrary small enough value to make sure the edges are sharp. And the period, let's say 1 over F in. So setting the period of this value as 1 over F in, it means that we are interested in running the input voltage transitions within our bandwidth of amplifier. So for the amplifier, because the bandwidth was 10 megahertz, larger than 10 megahertz, so 1 kilohertz is totally good enough. And now we can run the simulation. And we have to make sure this input is now changes to V pulse. And if you run the simulation, okay, and we can plot transient simulation, then we get this input voltage nicely, changing from 0.1 volt to 0.6 volt. And if you plot output node, then you can see that output node follows the input transistor nicely, except for this one, right? Lower state. So all of you guys, have you run or simulated this stage, this transition stage? Then do you know what is happening here? why this one is satisfying very well for high voltage, but it cannot follow the low voltage values. Did you figure out, or did you happen to see different waveform rather than this? Was this the similar?
Worst.
Worse. Because we don't have enough time for today. Let me explain. So the reason why we are facing this kind of transition mismatch for the especially low value is because of the DC operating point. So you can see that this DC voltage and DC simulation, maybe I should write down here. So shift, scroll, it goes to horizontal zoom. Control scroll, it goes to vertical zoom. And X plus light drag, it goes to horizontal zoom. I guess it was V. Right drag, vertical zoom. So I am trying to zoom in this area. So either you can use X plus right mouse drag, you can zoom this area, or if you want to zoom this specific area, you can press Shift and mouse scroll, and you can zoom in. For the vertical value, you can press Control, mouse scroll, or vertical value, I guess if you press V. Oh no, sorry, I guess it was a Control. Yeah, Control. It's not V, Control, right drag. So anyway, what I'm going to say is that the DC operating point is simulated specifically based on the starting point of everything, the transient simulation. So we started our transient simulation by setting the input voltage of low voltage 0.1 volt, and it switches with the rise time of 1 nanosec to 0.6 volt. So DC operating point is calculated based on 0.1 volt. So what happens is 0.1 volt here, and the buffer circuit is configured like this. So what I'm going to tell is that you can see that there is a significant drain voltage mismatch for this current meter, right? The drain voltage of current meter output is 120 millivolt. Drain voltage of the diode side, it is 600 millivolt. So remember, if you recall back to basics of IC design, current meter and the current meter mismatch or accuracy, if there is a significant drain voltage mismatch, then the current meter does not work as we intend. So that is the reason why we study about cascade like this. Oh, not this one. Okay, so when you set cascade configuration like this, then its drain mismatch is reduced. Your current metering mismatch is reduced, and the current meter accuracy is improved. In this case, you can improve the transient simulation accuracy. But for this kind of very simple circuit, there is no way around to further reduce this mismatch as good as this high voltage. What happens for the 600 millivolt? Of course, because we are applying 600 millivolt here, then output voltage follow 600 millivolt. Then it is more closer to the diode voltage here, 600 millivolt. Then the current metering accuracy is improved a lot. That is the result, what we can see at this node here. Okay, so finally, let's calculate our slew rate. For the slew rate, there are multiple definitions, but for the definition of slew rate is the behavior where the amplifier is stuck at the maximum speed. So it becomes more linear rise up rather than exponential or small signal. So there is a limit right here, linear curve here. By measuring the slope of this curve, you can approximate the slew rate of the rising slew rate. So you can use A and D, roughly measure the slew rate, which means like it is higher than 12 volt per microsecond. So it means a megavolt. Mega means 10 to the power of 6. So megavolt per second is equal to volt per microsecond. Micro is 10 to the power of -6. So it goes to 12.5 volt per microsecond rise time slew rate. And similarly, you can also measure 4-time falling edge slew rate like this. So it has a slope limit because this edge is too sharp. So this curve cannot go fast enough to follow up this sharp edge. That is what happens when you study about the slew rate of the amplifier. So it goes to almost the same, like 12 volts per microsecond. Let's go back to our template. It satisfies rather than 1 volt per microsecond, right? And based on this result, you can attach some screenshot of, for example, here the amplifier. Here changing to component parameters. You can just take a screenshot of this and attach to, what is happening? Okay, attach to here and test bench setup open loop AC as we did, and so on and so on. Okay, so sorry about the misunderstanding. So we will extend the deadline to the end of this week. So please submit within deadline and redesign the amplifier. Of course, I will post this lecture video, so you can just simply follow how it works for the CAD exercise. We will not degrade your score after deadline submission for this time. Before I conclude for today's lecture, let me talk about some important thing that is necessary to carry out CAD exercise 3. So let me run the AC simulation. I should run higher frequency and to 1 kilohertz to 10 gigahertz. So there is some weird behavior, right? I mean, we can observe that we have bandwidth here, and then it goes to like this. Suddenly it jumps back to some value here. This is not as we expect when we study about amplifier. So did you also observe this behavior when you run the simulation? Do you have any idea what is going on here? What will be the main cause? Yeah. Why this one doesn't go like this? Why this one go back to some value? So let me explain why this is happening. Because of the amplifier structure here. let me also plot phase of our amplifier. You can see that the phase of amplifier structure or the buffer it should look like 0 degree to negative 180 degree, right? But it goes back to 0 degree. And its amplitude also goes back to some value. So this means that there is some zeros. So we have pole at 3 dB bandwidth, but there is some zeros. So the mechanism of making this kind of zero is because of the CGS parasitic cap from input to output, because in our case, the input N is connected to B out. So there is a capacitor, CGS. There is a capacitor, CGS. At high frequency, it looks like those are a short circuit, such that input P and input N are directly connected to the output. And there is a load cap here. So there is a impedance-based voltage divider happens. That makes some, attenuation, like minus 15 dB attenuation. It is limited. So this can be verified by adding a cap 10 femtofarad, for example. And let me like this. Okay, and if you plot dB, you can see that its attenuation value is even increased from no cap to with 10 femtofarad cap, because there is a bit through of the parasitic capacitance. So to reduce this amount of attenuation, you should decrease the size of the transistor to make sure parasitic cap is reduced. For example, if you reduce width to 1 micrometer, then you will see the attenuation is even further down because there is a less parasitic cap. You can verify yourself. So anyway, this is the end of lecture today. So we will have a short break for maybe 5 minutes until 10:10. Then we will have quiz. Thank you.